So hello everyone, this is Ari from pantechelearning. So in previous session we saw SPI communication and we have developed the code for it. Okay. So today we are going to getting into a core concept which is ADC. So what is ADC? The abbreviation for ADC is analog to digital converter. So how it works? So when we take a temperature sensor, you will take for example, you will consider an analog temperature sensor which is LM35. Okay. So what it is going to do is, as per the temperature, it's going to give a voltage output. So the LM35 will give an input of the 3.3 volt. Then as per the temperature, the voltage is going to be getting varied, and the voltage which is going to be like diode, right? Like diode, when you increases bandwidth, it will conduct some electricity. So like that, according to the temperature sensor is emitting the current or voltage to the pin. So as per the what is the temperature? So we can it is ranging from 0 to 3.1. So it can when it is in the temperature of 50 degrees means it will give a voltage output of up to, we will consider make it as 2.5 volt. Like that it is going to be changing. So now we have to know what is the temperature here, right? So for this purpose only we are using a ADC tool. So analog to digital converter. So this what is going to do is it will convert ranging from 0 to 3.0 volt into a sum of the bits. What is the resolution you are giving? You are using a 10-bit resolution or 12-bit resolution. I will come to the part later, resolution parts. So we will make it as consider we will use a 10-bit. Okay. So what is the sum of the 10-bit? So the sum of the 10-bit is 1023, right? It starts from 0 and sum of the 10-bit is 1023. So what this ADC is going to do is, it is going to convert the 0 to 3.0 volt range to the digital value, which is range from 0 to 1023. So this is the process what ADC is going to do. So like you can see it in accelerometers, speedometers, in bike speedometers, you can see the same process will be done in later bikes, so previous bikes. Now it has been changed into sensors, lots of sensors. When it comes to that, they have directly connected digital sensors there. Now, when in old bikes, you can see that we will we will read speed will be given the voltage only. Then the voltage is converted using the ADC, and it is converted to the digital value. By using the digital value only, we will be programmed the code that will give some output. Okay. For this purpose only, we are using ADC. Okay. So what is the ADC is going to do? Simple term, ADC is going to convert the voltage value into a digital value for microcontroller. Okay. That is the process of it. Okay. So now we will get into the registers. Before that, what are the things we have to do before configuring the ADC? What are the things we have to know? Get to the block diagram first. We have to know which bus it is connected. Okay. So in STMF4 we have 3 ADCs. So each channel will have each ADC will have 8 channels. Okay, from up to 0 to 16 channels also it is available. Okay. So it is connected in APB2 bus. Okay, its maximum frequency is 84 megahertz. But we are going to use this. We are going to use the APB2 as 8 megahertz. So we are going to configure for the 8 megahertz frequency. Okay. So then what we have to know? We have to know what are the pins, the ADC, because we have lots of channels, right? So you have to go to the pin diagram. So you can see we have an analog inputs here. So what I am going to do is I am going to configure the PA of 1 and PA of 2 as an analog input. Okay. So I am going to read the value from those pins 1. So now we have to know which channel it is, right? So you have to go to the data sheet. So before that, we have to know we have to know some of the features characteristics before configuring the ADC. We have to know what is the maximum frequency can it operate and what is the minimum frequency can it operate, and where the channels are present, which pin it is present. So we have to know all these things. So first we will see where is this pins are. Okay. So in datasheet we have pin description. Okay. So we are going to use this PA1 and PA2. So in PA1, we have an ADC of, we can configure any ADC 1, 2 or 3. We are having a channel 1 in PA1 and channel 2 in the PA3. So we are going to use these 2 pins. So you can see this. You can see what are the channels in which pin. So we are going to use these 2 pins only. Okay. Then we have to know about characteristics, right? So we go to the data sheet again. So in this you can see we have an ADC clock frequency. So the minimum is 0.6 and the maximum is 36 megahertz. Okay. So the ADC can work at the maximum frequency of 36 megahertz. So what is the thing we have to do? We have to set the frequency below 36 megahertz. Okay. So I'm going to use this. I'm going to use the 4 megahertz of frequency. Okay. So and we have another option. We can use this up to 2.4 volt, or I'm going to use this maximum of 3.6 volt. Okay. So next what we have to do? Next. Now we have seen what is the maximum frequency the ADC is working and what is the pin we have to configure. Okay. So we will. So we are going to see the registers. Before that, what are the registers we have to see? So now we will see the steps for configuring the ADC. So these are the functions we are going to create. So system clock. So we are going to configure the PB to P clock 2 as an 8 megahertz. Okay. Then we are not going to use the PLL in system clock. We are going to directly use the HSC main crystal for the peripheral clock source. Okay. Then we are going to create the ADC unit function, and we are going to create for ADC enable and disable, and for starting the conversion. And we are going to also create a wait function, and we will get the data. Okay. So next, these are the things we have to do. Now we will detailedly see it. What are the control registers? What are the registers we have to work with? Okay. So guys, now you can convert this into masterclass into an internship. So 1 month internship on the embedded systems. So the fees is 1,200 guys. So discount is 509. So apply use this coupon code ESMC1 to get this offer. So the final fees is 691. So when you compare with this live and internship, the internship is going to be very advanced and detailed manner. And in every Saturday class, you're going to have one-to-one session. And we are going to add lots of projects to the internships. And we are going to expand the topics. So guys, use this internship opportunity to upskill yourself. Okay. So guys, what are the benefits are? You will get a 30 days of live session recordings. So it will be access for 90 days. And we are going to do some hands-on embedded projects. And while you are developing, you can ask my questions to me directly in mentor live sessions. We will given 6 mentor live sessions, which has been one is already over in past Saturday. So guys, register now. So you can attend this Saturday's live class with me. And after registering, you will get an internship confirmation letter, and you will get 2 e-certificates. One is for participation and another one is for completion. Okay, guys. So the fees is 1,200. The coupon is ESMC1, and the discount is 509, and the discount price is 691. Okay. So use this link to register, guys. So the link will be provided in the chat box, guys. So click this link and register now itself. Okay, so the batch 2 is going to end within this Friday. Then the batch 3 will get started. So guys, use this opportunity to attend the class and develop yourself. Okay. Okay. Now we will get into the topic. So first we have to create an initialization for ADC. First we have to enable the clock. We will enable the clock for ADC and GPIO. Then we have to set the prescaler value. So what is the prescaler value? So if I can say, I'm going to use a P clock as an 8 megahertz. So it is not an issue. So if take a scenario that the P clock is at the maximum frequency of 80 megahertz. So the P clock 1's maximum frequency is 42 megahertz. When it's come to P clock 2, its maximum frequency is, wait, I will show you. So you can see. So you can see the maximum frequency 42 megahertz and the P clock 2's maximum frequency is 84 megahertz. Okay. So So what we have to do is the maximum frequency for the ADC is 36 megahertz, right? So if I am configure this 84 megahertz as a use the 84 megahertz as a peak of 2 means I have to reduce the value to work with ADC. So for that purpose only the prescaler is used as like same concept used in PLL, like PLL, the PLL having prescaler, like that same thing we are having a prescaler for ADC also. Okay. So in our case it is a not issue. We are going to use the 8 megahertz of frequency and our ADC is connected to the APB2 bus. Okay. So we are going to use it in the 4 megahertz of frequency. Then we have to select the scan mode and the resolution. Resolution means we are going to configure in the ADC in a 12 bit, 10 bit, or 8 bit, or 6 bit. We have 4 options. Okay. So we can use anything. I am going to use this 10 bit resolution. Okay. Then we will set the continuous conversion, end of the conversion, and data alignment. Data alignment means to which part. If I choose some 10 bit resolution means we have a 32 bit of world length, right? So where the 10 bit must be in the LSB, from LSB or MSB. So I'm going to use it from LSB. So I'm going to align the data to the right hand side. Okay. Then the data set the sampling time. Then we have to set the sampling time, the time for each conversion. Okay. Then set the regular channel sequence length, and we have to finally set the GPIO model register as an unlock. Okay. So these are the things we will do in the initialization settings. Okay. So next we will create a function for ADC on and off, and we will create a start sequence. So we will set the sequence and start the conversion, and we will wait for the end of the conversion to set, bit to set, and we will return the ADC data, and we will print or we will see it in the debug output. Okay. Okay. Now we will get into the KEIL ID. Okay. We will develop the code for the ADC. Okay. So we are going to read the channel in PA of 1 and PA of 2. Okay. So we will go to the KEIL. So now we have to select the package. So create a .c file. Then okay. First we have to include the header. Okay. So we are using is F07. So what are the things we are going to create? We are going to create void of system clock. Then we are going to create a ADC init. Then we will enable the ADC. You will get a function for enabling the ADC. Then disable the ADC. Then we have to start the function, ADC function, right, for the void of. So we are going to give a parameter as channel. Which channel we have to measure. Okay. So we will send the channel. Okay. channel. Then we have to create a wait function for ADC. Finally, we have to get the data, right? So we have to get the data. Now we will create these functions. Okay. So when come first, before that we will get into the cube MX. Okay. So I'm going to use the HSC as a main clock for main source for the system clock. So 8 megahertz. So I'm going to use the P clock also at 8 megahertz. So I don't need to give a prescaler for AHP prescaler and these two prescalers. I can configure these things. Okay. So first we will first we have to enable the power clock interface. So RCC out. Yeah. So this will enable my power clock. Then we have to tune on the HSC main crystal, right? So for the RCC off, it is in the control register. So this already I have shown in the previous session itself. I have shown you all these registers. Okay. So here I will do it faster. So this will tune on my HSC. Now I will check whether the HSC is tuned or is set down by checking the flag. The flag is in 17th bit. Then we have to select the HSC as a system block. So go to the configuration register. So this will set my HSC as a system block. Then I have to check whether the HSC is selected as a system block or not. Okay, so I will check it in the same configuration register. It is in the flag is in the second bit. Okay. So now we have created the system clock configuration. Okay. So next thing we have to do is we have to create a function called ADC initialization. Okay. So void of right. So what is the first thing we have to do? We have to go to the ABB2 register. So you can see we have an ADC1 in 8th bit. So we have to send the logic 1 to the 8th bit to enable the ADC clock 1. Then we are going to use the port A, pin 1 and 2. So we have to enable the clock for GPIO A. So GPIO A is in 0th port. So we will send logic to this and okay. So RCC out. So this will enable my GPIO clock for A. Then I have to enable the RC node ADC1 clock, right? So it is in the APB 2 ENR. It is in the 8th bit. So now we have enabled the clock for ADCs. Okay. Then now we have to set the frequency for ADC, right? We have to say what is the frequency it is. We have to set the frequency. We have to set the prescalars value. So we go to the registers. We will see the registers. Go to the common control register. So you can see we have an ADC prescaler here. So what I'm going to do is I'm going to use divided by 2. So I'm going to use the ADC in the 4 megahertz of frequency. Then I have to send the 0 to these 16th and 17th bit. Okay. So we will send it. So ADC of I'm going to send 0 to those bits. Okay. '16 and '17. So now we have set the frequency, which is 4. So ADC frequency is 4. Okay. 4 megahertz. Then next thing we have to do is we have to select the scan mode and what is the resolution. So as I said, the resolution is we are going to use this 10-bit resolution. So go to the control register. So in this register you can see error show. We have an 8th bit as a scan mode. You have to enable the scan mode. Then so we have a 24th and 25th bit for selecting the resolutions. So what is I'm going to use this 10-bit resolution. So it is sum of the values 1023. When we are using 12-bit means it will be the sum of the values 4095. Okay. So I will send the logic 1 to the 24th bit to use this 10-bit resolution. Okay. Then I will send the logic 1 to the 8-bit to the scan. Okay. So ADC of left shift of 8 to enable the scan mode. Then I will select the 8-bit resolution. I will left shift the 1 to the 24th bit to select the resolution as a 10-bit. Okay. So next thing we have to do is we have to set the EOC and CC, which is a continuous conversion and end of the conversion. So go to the same control register, you can see. So you have to go to the control register 2. In control register 2, you can see. So we have an end of conversion and continuous conversion. Okay. So this is if I set this logic 1 here means it is going to continuously convert those values. Okay. So you will set logic 1 to the 10th bit and first bit to enable the CC and EOC. So ADC of 1. This is now continuous conversion and end of the conversion in 10th bit. Then what we have to do? We have to say to align in left or right. Okay. So go to the register. So we have in control register 2, we have a data alignment. So I'm going to given right alignment. So it is going to save it from the LSB. Okay. So I have to send logic 0 to the 11th bit. So ADC of 11th bit. Okay. So now we have right alignment. We have started the right alignment. Okay. So next is we have to set the sampling time. Okay. So for that you have to go to the I will show the register. Go to the sampling time register. So in this we will have a channels from. So this is a sampling time register. One is from 10th pin to 18. So we are going to use this 1 and 2. So we have to configure these two pins SM2, SMP2 and SMP1. Okay. So we are going to send the cycle. So if this is a sampling time is going to say so for conversion how much time it is going to take. Okay. So you have to say the sampling time. So I will simply give a 0 to these two channels. So I will shift the 0 to the sixth bit and third bit to select these two channels because we are using is channel 1 and channel 2. If I am using channel 3 means I will send this logic 0 to this. Okay. So this is a sampling which is going to say how much time it is going to take for the conversion. Okay. So we will simply say the 3 cycles. So we will send the yes, please register. One left should of 3 and 6. Now we have set the sampling time. Then next what we have to do? Next thing is we have to say how many channels we are going to use. So I'm going to use one channel, two channel, or I'm going to configure all this. I'm going to use all the ADC channels. So we have to say how many channels we are going to use it. Okay. So for that you have to go to the regular sequence register. In that you can see in the regular sequence register 1 we have an L. So what is the length of what is the sequence length? So if I'm using the two channels means I will give an 2 here. If I'm using 16 channels means I'm going to use all the 16 channels means I will give this I will set logic 1 in these 4 bits. Okay. So now I'm going to use only 2 channels. So I will send the logic 1 to the 20th bit. Okay. So this is going to say that I'm going to say the microcontroller that I'm going to use the 2 channels. So I'm going to I need to read the 2 channels value. Okay. So next we have to set the motor register. So go to the GPIO registers. So in this, what is the pin we are going to use is 1 and 2. So then I have to send the logic 3 to the second bit and fourth bit. Okay. So then the pin 1 and 2 will get set in the analog input mode. Analog mode. Okay. So you can see here analog mode has a logic 1 which is the sum of the values 3. Okay. We will send the left shift the 3 to the second and fourth bit. Okay. GPIO. So in motor register. So now we have finished the ADC init function. Okay. So then what we have to create? We have to create the enable and disable. Okay. First we will create a code for enabling. So for enabling, you have to see the control register 2. Wait. So you can see we have a 30th bit as a start conversion, and we have enough 0th bit as an ADC on. Okay. So now we have to send logic 1 to the 0th bit to tune on the ADC. So ADC off. So this will on the ADC. Okay. So for disabling, you have to send logic 0 to this bit. Now we have created a function for these both. Okay. Then we have to create a function for start and wait and get data. Okay. So first we will write a start function. So in start function, first we have to go to the register of SQR wait. In this, we will have an up to 16. If you are configuring 16 channel also means we have to set all these 16 also. So the regular sequence is as a 3, 1, 2 and 3. So now I am going to use this pin 211. So I have to configure the SQR register 3. Okay. So this is the thing which is going to say in which channel it has to conversion has to happen. Okay. So we will. So if I'm configuring, if I'm checking the I have to do conversion in the first channel input means I have to send the logic 1 to this register to the 0th bit, and if I want to use the second channel, I have to do the conversion second channel means I have to send the logic to the 5th bit. Likewise, if you want to configure all the 16 channels means all the 16 channels have to do the conversion means you have to send the logics to all the bits. Okay, first we will use only two pins, so we will configure this SQR3. Okay, so first ADC off. First we will reset it. Then now we are going to give the channels parameter. Okay, so we are going to say whether the if I give 1 year means it is going to read the value from the first channel. If I going to give the 2 means it's going to read the value from the second channel. Okay, so that is the purpose we are using this register. Okay, so ABC off. So we have already mentioned the channel. So we will shift it to the 0th bit. Okay. Okay. So then we have to now we will make the status register. We will reset the status register. Then we will start the conversion. So now we have to start the conversion. For that, go to the control register 2. So we have a 30th bit as a start conversion of the regular channels. Okay. So we will send the logic 1 to this ADC of 1. So this will start my conversion. Okay. So then what we have to do, we have to create a wait function, right? So for wait function, we have to go to the status register again. So in this you can see we have an EOC flag. So if the conversion is ended, then the flag will be given in the logic one will be get set in this bit one. Okay, we will check with this bit one. So it is going to wait till the conversion is till the end of the conversion bit is get set in. Okay, then we have to get the data. So we will return the one of data register. Okay, so now we have returned the data registers value. So we have created the functions. Okay, now we will. Now we have to create the main function. So I will create a main. While the first thing we have to do is we have to initialize the system. Before that, I'm going to create a variable to store the values of the ADCs. Okay. So first we have to initialize the system clock. Then we have to initialize the ADC. Then we will enable the ADC. Now we will create a while. So inside while we are going to start the ADC conversion. ADC of start conversion. Then we will wait till the conversion is getted to wait till the EOC bit is get set to logic 1 and we will read the value then. Okay. Then we will read the value to the we already declared my data value. Okay. So my data. ADC of so we will read the value for. So before that we have to say the channel, right? So we have to say send the parameter which channel we are reading. So I'm sending 1 here to read the channel 1. Okay. So I'm storing it in the 0th index. Then I will read the channel 2. Start off. Then I will wait for the end of the conversion. Then I will store the read the main data. Okay. In the first instance. Okay. Okay. So now we have created the code for ADC. Okay. we have no errors. Now we will import this code to the board. Okay. And we will see the debug out. So before importing the code, we have to select the STM debugger. Now we will upload the code. Okay. So the code is uploaded. Now you can see the debug. So go to the debug. So run the program. So first we have to connect the PA1 and PA2. Okay. So we will connect those pins. I will do the input to the. So now we will read it. So you can see we are getting a channel 1 as an 1023 because I have connected the PA of 2 with the 3.3 volt of input and I have grounded the PA of 1. So what is the resolution we are using? We are using is 10-bit resolution. So the sum of the if the 3.3 volt is the maximum value. So the maximum value means it's going to give the maximum digital value. So what is the maximum digital value? It is going to be sum of the 10 bits. So sum of the 10 bits is 1023. So now we will change the pins. We will. So you can see now that I have changed the pin. I have connected the 3.3 volt to the PA of 1. So this is how the values will be changed. If you want to we want to check the logs of all the channel pins, you can use this code and develop this code. Okay. Okay. So guys, if you want to configure the temperature sensor means you can use this method also. Okay. So guys, I think code is understand. Okay guys. Okay, thank you.